Welcome today. We explore the world of descriptive statistics. In this session, we will study two main areas: measures of central tendency, which include mean, median, and mode, and measures of dispersion, such as range, variance, standard deviation, and interquartile range, which describe how spread out the data is. Hello everyone, we are Sanika Campbell and Sidi Pardeshi, and our presentation today is guided by Dr. Dipti Patil. In today's presentation, we will begin with an introduction to descriptive statistics, discuss its key components and its role in the data science pipeline, explain each concept with examples, explore real-world applications, and conclude with key takeaways. Let's get started. So, what is descriptive statistics? It is the branch of statistics that summarizes and describes the main features of a dataset, using numerical measures as well as visual representations. It has two main components: measures of central tendency, which show the center of the data, and measures of dispersion, which show how the data is spread. Descriptive statistics play a vital role in the data science workflow, from initial data assessment to model preparation. They help ensure data quality, reveal useful insights, and improve model performance. Data cleaning and preparation are essential in any data project, and descriptive statistics guide this process. First, missing values are handled by calculating the percentage of nulls in each column to decide on imputation or removal. Next, anomaly detection uses minimum and maximum values and standard deviation to identify suspicious data. Then, consistency checks compare distributions across datasets or time periods to ensure data integrity. Overall, descriptive statistics help measure data quality and prepare it for accurate analysis. Exploratory data analysis focuses on understanding data using summary statistics. Descriptive statistics turn raw data into meaningful insights by showing typical values, variability, and patterns. Summarization reduces large datasets into clear metrics. Distribution analysis reveals whether data is normal, skewed, or multimodal, and pattern analysis helps identify relationships between variables for data-driven decisions. Feature engineering is vital for building accurate models, and descriptive statistics support this process. They help create meaningful features by summarizing data, scale, and transform features using distributions and variance, and handle outliers with measures like IQR and standard deviation. This ensures the features are informative and improves model performance. Let's see definitions. Let's talk about the mean, one of the most common measures of central tendency. The mean is the average of a dataset and represents its central value. It is calculated by adding all the values and dividing by the total number of observations. The formula is x bar equals the sum of all values divided by n, where x bar is the mean, xi represents each data value, n is the total number of values, and the sigma symbol means summation. The mean helps us understand the overall trend of the data and makes it easier to compare different datasets. Now, let's talk about the median, another important measure of central tendency. The median is the middle value in a dataset when it is arranged in ascending or descending order. It divides the dataset into two equal halves. If the number of values in the dataset is odd, the median is simply the middle value. Mathematically, for an odd number of values, the median is the value at the position n plus 1 divided by 2. Here, n represents the total number of values in the dataset. If the number of values is even, the median is the average of the two middle values. For an even dataset, the median is calculated by adding the values at positions n by 2 and n by 2 plus 1, then dividing the sum by 2. Finally, let's talk about the mode, the third key measure of central tendency. The mode is the value that appears most frequently in a dataset. A dataset may have one mode, which we call unimodal, more than one mode, called multimodal, or sometimes no mode at all if all values occur with the same frequency. Understanding the mode helps identify the most common value in a dataset, which is especially useful in statistics, business, and everyday decision-making. Let's see how measures of central tendency work using an example of students' heights. Here we have the heights of 9 students in centimeters: 154, 139, 154, 192, 180, 140, 154, 155, and 192. The data value that appears most frequently in a dataset is called the mode. Looking at these numbers, we can see that 154 appears 3 times more than any other value. So, the mode of this dataset is 154 centimeters. This means that 154 centimeters is the most common height among these students. Sometimes a dataset may have more than one mode or no mode at all, but here, 154 is clearly the most frequent value. Here we have a pie chart representing the top values in our dataset. The mode, which is the value that appears most frequently, is 154. It occurs 3 times, making up 33.3% of the data. Identifying the mode helps us quickly see the most common observation in a dataset. The median is the middle value in a dataset when all values are arranged in ascending order. When arranged in ascending order, the dataset becomes 139, 140, 154, 154, 154, 155, 180, 192, and 192. To find the middle value, we use the formula n plus 1 divided by 2, where n is the total number of data points. Since there are 9 data points, the middle position is 9 plus 1 divided by 2, which gives us 5. So the fifth value in the ordered dataset is 154 centimeters, which is the median, representing the center of this data, and this value helps us understand the typical height in this group. Let us see an example where we have 10 values in our dataset. The position of the median is calculated as 10 plus 1 divided by 2, which equals 11 divided by 2, resulting in 5.5. Since 5.5 is not a whole number, the median will be the average of the fifth and sixth values in the ordered dataset. Our dataset is 139 centimeters, 140 centimeters, 154 centimeters, 154 centimeters, 154 centimeters, 155 centimeters, 180 centimeters, 192 centimeters, 192 centimeters, and 196 centimeters. Here, the fifth value is 154 centimeters, and the sixth value is 155 centimeters, so the median equals 154 plus 155 divided by 2, which equals 154.5 centimeters. If instead we have 9 values, the position of the median becomes 9 plus 1 divided by 2, which equals 10 divided by 2, resulting in 5. Here, the median is exactly the fifth value, which is 154 centimeters in this dataset. By finding the median, we can quickly understand the central tendency of our dataset, giving us insight into the typical value without being affected by extreme values. On the left, we have a sample size of n equals 10. Because 10 is an even number, there is not a single middle data point. Instead, the median falls exactly halfway between the fifth and sixth values. In this specific dataset, that calculation gives us a median of 154.5, and you can see how that green line sits right between our primary data clusters. Now look at the plot on the right where we've removed one data point, making n equals 9. With an odd number of values, the median is much simpler to find. It is simply the middle most value in the list, the fifth value. Here our median is 154. Next we look at the mean, also known as the average. It finds the center of a dataset by equally distributing the total value across all observations. The sigma symbol in the formula means summation, or add all values. The process has 2 steps. First, add all data values, and second, divide the total by n, the number of values. For our dataset with n equals 10, we add all measurements from 139 to 196 and divide by 10, giving a mean of 165.6 centimeters. This value, called x bar, represents the mathematical center of the data. From the histogram, most values lie between 140 and 155 centimeters, where the median is 154.5. However, the mean shifts to the right at 165.6 because it is influenced by higher values like 192 and 196. In this section, we are going to understand measures of dispersion, which tell us how spread out our data values are. While mean, median, and mode describe the center of the data, dispersion measures explain the variability. The main measures we will cover are range, which is the difference between maximum and minimum values; variance, which measures how far each data point deviates from the mean; standard deviation, which is the square root of variance and gives spread in original units; and interquartile range, or IQR, which measures the spread of the middle 50% of the data. Together, these help us understand data consistency and variability in data science. Now let us understand the first measure of dispersion, called range. Range represents the simplest way to measure how spread out a dataset is. It is calculated as the difference between the maximum value, which is the largest observation in the dataset, and the minimum value, which is the smallest observation. The formula is written as R equals maximum value minus minimum value. A higher range indicates greater variability in the data, while a smaller range shows that the data values are closely grouped together. Now let's understand variance, which measures how much the data values spread around the mean. Variance is calculated by taking each data value, subtracting the mean, squaring that difference, and then finding the average of those squared differences. The formula for population variance is written as sigma squared equals summation of xi minus x bar whole squared divided by n. Here, sigma squared represents variance, xi represents each individual data value, mu is the population mean, n is the total number of values, and the summation symbol means we add all the squared differences together. Squaring ensures all values become positive and emphasizes larger deviations. Now let's move to standard deviation, which is the square root of variance. While variance gives spread in squared units, standard deviation converts it back to the original units, making it easier to interpret. The population formula is written as sigma equals square root of summation of psi minus x bar, that is mean, whole squared divided by n. Here, sigma represents population standard deviation, xi is each data value, mu is the population mean, n is the total number of observations, and the summation symbol means we add all squared deviations. For a sample, the formula is s equals square root of summation of xi minus x bar whole squared divided by n minus 1, where s is sample standard deviation, x bar is sample mean, and n minus 1 is used for unbiased estimation. Now let's understand the interquartile range, or IQR, which measures the spread of the middle 50% of the data. Unlike range, IQR is not affected by extreme values or outliers. It is calculated using the formula IQR equals Q3 minus Q1, where Q1 is the first quartile, representing the 25th percentile, and Q3 is the third quartile, representing the 75th percentile. To find IQR, we first arrange the data in ascending order, then identify Q1 and Q3, and subtract Q1 from Q3. A larger IQR indicates greater variability in the central portion of the dataset. Let's continue with previous example, first measure of dispersion range, which is given as max value minus min value in data. In our case, maximum value is 196 centimeters, and minimum is 139 centimeters. Hence, range is 196 minus 139, which is equal to 57. This signifies the total spread of the data from one extreme to the other. To calculate variance for the given dataset, the first step is to find the mean, which is the average of all data points and is 165.6 in our case. In the second step, we subtract the mean from each data value, square the result, and then add all these squared differences. This gives us the summation of xi minus x bar whole squared, which comes out to 4,404.40. In the final step, we calculate variance by dividing this value by the total number of observations, which is 10, giving us a variance of 440.44. Here we are looking at a variance graph, which shows the squared deviations from the mean. On the x-axis, we have the data values measured in centimeters. These represent heights, such as 140 centimeters up to 195 centimeters. On the y-axis, we see the squared deviation from the mean, which means how far each value is from the average. squared to remove negative signs and emphasize larger differences. Notice the graph forms a U shape. Values closer to the mean, around 150 to 160 centimeters, have smaller squared deviations, while values farther from the mean, like 140 centimeters and 195 centimeters, have much larger squared deviations. This visual clearly demonstrates how variance increases as data points move away from the mean. Now, to calculate standard deviation, we take the square root of the variance. Since the variance we calculated is 440.44, we find its square root. The square root of 440.44 is 20.99. This value represents the average distance of the data values from the mean, expressed in the same units as the original data. A standard deviation of 20.99 indicates that most data points lie about 21 units away from the mean, showing the level of spread in the dataset. We are looking at the standard deviation graph, which shows the actual deviations from the mean. On the x-axis, we again have the data values in centimeters, ranging roughly from 140 centimeters to 195 centimeters. On the y-axis, we see the deviation from the mean, which represents how far each value is from the average, but unlike variance, these values are not squared. Notice the pattern is similar to the variance graph, but the numbers are smaller because we are not squaring them. Values closer to the mean, around 150 to 160 centimeters, have smaller deviations, while values farther away, like 140 centimeters and 195 centimeters, have larger deviations. This graph helps us understand how spread out the data is in actual units. Now let's calculate the interquartile range, or IQR. First, we already found the overall median, which is 154.5. To find Q1, the first quartile, we take the lower half of the ordered data, 139, 140, 154, 154, and 154. Since there are 5 values, which is odd, the median of this lower half is the middle value, so Q1 equals 154. Next, for Q3, we take the upper half, 155, 180, 192, 192, and 196. Again, with 5 values, the middle value is 192, so Q3 equals 192. Finally, we calculate IQR using the formula Q3 minus Q1, so 192 minus 154 equals 38, which represents the spread of the middle 50% of the data. The IQR graph, also known as a box and whisker plot. The y-axis shows the values in centimeters, while the x-axis represents the data set. The box in the center represents the interquartile range, or IQR, which contains the middle 50% of the data. The bottom of the box is the first quartile, or Q1, the top is the third quartile, or Q3, and the line inside the box represents the median, which is the middle value of the data. The lines extending above and below the box are called whiskers, and they show the minimum and maximum values, excluding outliers. This plot helps us quickly understand the spread and distribution of the data. Descriptive statistics play a crucial role across multiple stages of the data science pipeline and business analytics. In exploratory data analysis, they help summarize datasets, understand distributions, and detect patterns before building models. For outlier detection, measures like IQR and standard deviation identify abnormal values that may negatively impact model performance. In feature understanding and selection, mean and variance help analyze how each feature behaves and determine its importance. During data preprocessing, these measures are used for normalization and scaling. In business and financial analytics, they support customer analysis, income trends, risk assessment, and overall performance evaluation for better decision-making. Let us understand a real-world case study based on Amazon sales analysis. Amazon regularly analyzes monthly sales data of electronic products across different regions to understand customer demand and improve product performance. The dataset includes multi-region sales data collected over multiple months, making it large and diverse. The key objective here is to identify average sales performance and understand typical demand levels using descriptive statistics. The data also involves complex variables such as seasonal trends, promotional campaigns, and market fluctuations, making descriptive measures essential for converting raw sales numbers into meaningful business insights. Now let's see how descriptive statistics are applied to Amazon sales data. Under measures of central tendency, the mean is used to calculate average sales per region, helping establish a baseline performance metric. The median identifies the most typical sales value by reducing the impact of festival or promotional spikes. The mode highlights the most frequently occurring sales range across all data points. Moving to measures of dispersion, the range compares the highest and lowest sales values to understand overall market variability. Standard deviation measures demand fluctuations and sales consistency over time, while interquartile range, or IQR, helps detect unusual spikes or sudden drops in monthly sales patterns. To conclude, descriptive statistics provide essential tools for summarizing and understanding the fundamental characteristics of any dataset. Measures of central tendency, such as mean, median, and mode, along with measures of dispersion, including range, variance, and standard deviation, work together to describe both the center and spread of data. These techniques form the foundation of exploratory data analysis. Thank you for watching.